So this is recording to introduce how to calculate a wind load the on a week 4 tutorial. This is the wind load calculation for part of frame. So basically, the plan here is that we have those part of frames marked in red. And they just sit across the buildings. As we can see, they support a roof, and this is called a podium. This is called a rafter. This is a very integral part frame. So it's standing on the infrastructure here. And the setting is that we have 31.2 meters here. We have 31.2 meters here. That's it. So we need to calculate wind load. The assumptions for the project stage 2 is here. We're going to first stick to the plan. And as we say that we were firstly given the design wind load P on the roof, so this is the formula we use here, and we get the density of the air is 1.2 kilograms per cubic meter. So this one is finished, and also the wind load is given as 35 meters per second, and we double it. So, and also the dynamic factor is determined as 1.0. So generally speaking, we have this one, and this determined. The only thing that is not determined is CIV figure, and those two, and those other things has been determined as as 735 multiplied by this fig. So the only thing left is to determine this. And determine this aerodynamic shape factor. First, determine the internal pressure, as we demonstrate here. It has two parameters. The first one is negative 0.2 or 0.0. It's determined from table 4.1a. That's generally, I think that's generally here. Yeah, we get it 0.18. That's because we've given in the brief that the building is perfectly sealed and have no opening windows, so the parameters negative 0.2 or 0.3, 0.0. We get back here. So that thing is determined here, and the combination factor is determined as 0.8 because it was given in the brief that we have 4 effective surfaces, and it was determined in the chart. I think it's here, because the thing is that the load, this is the building we're dealing with, and the load comes in this way, and this is the part of frame that we're talking about. So in terms of that part of frame, the wind is coming in the left hand side, and this is 4 effective surfaces, and that's why we pick the internal at 0.8 and correspondingly we have external at 0.8. And in terms of the external pressure, we determine this from the node that I have given, and this one is that's the local vector. This is 1.0, and Kp is 1.0. This is cladding vector, so it's cancelled out. The only thing left is Ka, which is the error reduction vector, and this is the Kce, which is the combination vector, and this is the external coefficient. So in determining of this, we find for wind wall 0.8. This comes from okay, so this row, we have the windward wall, and apparently our H, the height of the building, is determined as the 3.0 blah blah plus 4.05, as given in the brief, and that height is actually taken from the midpoint of the building, mid height of the building, as I draw here, and this is actually the 3 point blah blah, and the height of this is 4 point blah blah, so that they sum up as the average. And it was calculated as smaller than 25 meters. And also, these structures we see we've always spelled it on an infrastructure here. That's why we call it a elevated building. That's why we choose 0.8. For the other thing, the leadwood wall, which is the portal frame here, and the wing is acting away from that. We get wing direction. It tells us to see figure 2.2, and figure 2.2 is here. So let's say this is our building, right? And wing below is here. So in this direction, we call theta equals to 0. That's the 0 direction. And then, so therefore, we pick this range. Okay, so this range. Hippo gable. The hippo gable is listed here, and the thing we're dealing with is the gable. And this gable, we continue the roof pitch was 3 degrees, smaller than 10 degrees, and D and B, D over B is demonstrated here. Demonstrated here because the wind comes from that direction. Therefore, the portal frame is situated here. Therefore, this is B and this is D. So the B is actually calculated from the plane view. From the plane view of here is it's 31.2, and D. I need to check. The where's D and B? Okay, perfect. So this is the thing that we're dealing with, and we're actually talking about B of one portal frame because we have a lot of portal frames here. Let's see, this. So in terms of that, the B is we're talking about, and the D, as a matter of fact, we talk about D in the span of the portal frame. And we calculate D over B. As we can see in the calculation, D and B is 31.2. That is actually the depth here. It's here, and the B is 46.8. It's mentioning that. Sorry, I'm wrong. So, in terms of B, we're calculating the entire length, and it's given at 46.8. So that's why we're dealing with this span. So this D over this B, D over B. Okay, so we have calculated that this is 0.67. And if that is the case, we come back to the chart. To find S more than 1. That's why the external pressure coefficient is determined as a negative 0.5. Okay, we continue to the roofs. The roofs, we have the cross wing slabs for gable roofs because we're dealing with gable roofs, so all alpha. And horizontal distance from the wing edge of the roof, it actually means the portal frame is here. And we set a distance, for example, this is X. Next, in a range of 0 to 0.5 height. The height was determined previously, as shown here. Therefore, we plug in the value of h here, so we calculate the x here. And if it is that range, we gonna say that in this part, the wind load is gonna be some value, and also in this part, it's gonna act in this value. The most important thing is that we square that street edge, which is we say it's from calculation. I think it's 15. It's 10 something, so approximately here. And from here to here, we get the same wind load as 90.34 kilonewtons. And that's demonstrated here. Let's see, it's demonstrated here. So that's why from here on, we have 94.09. Okay, and then we talked about the combination factor. It was the same derived from that chart as we talked about in the 4 effective surfaces. It's also 0.8, so get rid of that. And also the error reduction factor was determined as 0.8 because the trapdoor area was was here. And when we talk about traffic area, let's see the standard. So it's here, and the traffic area is just the roofs and side walls. And this roof, we're actually talking about this. Sorry about that. Roofs side walls, the side walls in terms of wind of the wind direction. So that's demonstrated here. So if that is the wind direction, and this is the wind wall, and this is side wind wall, and the roof is actually what we're trying to calculate. The roof here is demonstrated in plain view. Okay, so this roof, there is a small roof here. There's also a big roof here. There's also a roof here. And this same state that we project on to calculate the traffic area. And as we say, this is 31.2, this is 46.8, so the multiplication produced like somehow greater than 1,000 square meters. So the area reduction factor we apply here for the roof is 0.8. And if this 0.8, we're gonna just put it here. And so just know that this 0.8 is only for roof because it was mentioned, as we say in standard just now. And then we get two cases, and we just transfer that parameters here into this chart, somehow like chart. Because we have two different internal loads, this 0 and this 101 7.6. That's it. But just know that in this way we are still dealing with the kilopascal. When you transfer the kilonewtons to apply the UDL, which is going to be composed of the live load and that load and the subsequent calculations. So in this one, the methodology that we transfer kilopascal to kilonewtons is that we multiply the length of that, and this really depends on what kind of structure members that we care about. So in this one, we calculate columns. Columns is here, and we calculate that based on half length of the left of the. So this is a whole part of frame, okay? Yeah, because this is one part frame, this is one other, and one part frame takes the load from each roof and the side walls. So this part of frame we're talking about here is taking the load from half of its left and half from its right. So that's why if we calculate the column, the UDL, the column, this i.e. we're talking about kilonewton per meter, and we multiply this length. We're dealing with the rafter, which is generally the same thing. The rafter is here. Sorry, it's here. It's the roof. This is the rafter. So we're gonna multiply the length in this area. In this direction. That's it.